Hi, my name is Tovio Roberts, and this is a Galvanize data science prep study hall. Sorry for the delay. I think we're roughly 10 minutes behind. Just trying to iron out some bitrate stuff with the stream itself. Let's look at a couple of the questions in Slack. Yeah, I'll just take a look here. So if you're in the Slack thread and you can hear me and everything looks okay, just give me a quick thumbs up. And then I'll get to answering some questions. All right. Yeah, there's a question in here. Type within the dictionary and why we would maybe use enumerate. Okay, so let's think about that. Let's think about the enumerate function. So enumerate just looks like this. We often will use enumerate to traverse some kind of list of things. So I'm just going to break this out into a fairly simple problem first. Let's do brick, concrete, wood. Let's do, I don't know, porcelain. That's probably not how you spell porcelain. Yeah, let's pretend that's how you spell porcelain. And I don't know, plastic, vinyl. Okay, so let's just look at what enumerate gets us if we run this on this list. So let's just print the output of this list and get a sense of what's going on here. So Python delme.py. That gets us an enumerate object. Let's see if I can get something more out of this. I'm going to try casting it to a list. And let's just take a look at what this is. So notice this is giving us an association of an index to each item of the list, right? So if we were to iterate over this, we can unpack this tuple during iteration. That's just kind of a nice way to think about it. So this is a list of tuples. That's what we're getting out of enumerate. What I can do here, I can start the enumeration at a different value. And all this is going to do is shift this 0 over a little bit. And I'll make the comparison here between the two. So instead of brick being associated with 0, brick is now associated with 1. Now this might look kind of familiar to some other things, right? This might look like what we might see out of a dictionary. So what I'm going to do here is I'm going to create some kind of analog using a dictionary. I'm going to say for item in list. Well, let's do it like this. For index and item in enumerate list. And let's start that at 1. So I'm going to kind of recreate what we have here, this 1, brick, 2, concrete, etc. I'm going to collect this into a dictionary. And I'm going to say d sub index is going to get the item. And if I print the dictionary, we'll see kind of this association through the dictionary itself. And that looks something like this. So obviously this is not a list. This is different from a list. But we can get back to a list pretty easily. We can print d.items. and this is going to unpack what we've got here. And just something to notice, what we get out of d.items is not exactly a list, but it's not a list. Does that make sense? It is a dictionary items object, and it looks something like this. So this and this are effectively the same things, and if I were to cast this to being a list, they'd be exactly the same thing. You know, we're not looking at a dict items object anymore. We're looking at a list of the items in a dictionary. You know, maybe that seems like a minor difference, and it is for our purposes, because both a dict items structure and this list of tuples, we operate on them in essentially the same way. So we could take this and we could throw this into this enumerate position up here, and actually let's keep that, and this should still work for us, right? Because we're unpacking each of these tuples into index and item, and we get the same output, right? We get this dictionary items object as the output. Now this is just some underlying concept here so that we can think about enumerate in context of what it actually is. So this is just some list. Great. We can make this more of a numeric problem. I think that might be more interesting. Let's get a range of numbers from 0 to 100, and let's go by 3. And I don't have to do this, but I'm going to cast it to a list. And let's just, I'm going to call it numList, and let's print the numList. Let's just see what we have. So looking at this, we get 0 to 99 going by 3s. That shouldn't be too surprising. I think it's, I think it makes sense that we would get that. So let's say I want to process this list. So let's process the list, and let's say by multiplying each item in the list by its positional value plus 1. Okay? And to do this, it'll be convenient to have an association between the positional value and the item in the list itself. So, you know, we know what this looks like. We start at 0. We'll multiply 0 by, let's do over 6. So let's make this the operation. So the positional value plus 1 divided by 6. Let's do that. So it'll be 0 times 1 over 6, 3 times 2 over 6, 6 times 3 over 6, and so on. So let's just write this out. And I'll make this into a function. So let's do process dictionary, process numbers. And let's give this a starting position, and let's default that to 1. That's going to be value plus 1, right? Or value plus n, value plus starting position, however we want to think about that. And we're going to pass in a list of numbers, and I'll just call it list. So thinking about this, let's make just a new accumulator called new list, just a list collector. And we'll go ahead and say for num in list, we're going to do something to each number. Now we could do this a couple ways. I could say you know, well, I've already got starting position. So what I could do is say new list is going to get the, let's see, oh, we do need a counter, I'm sorry. So I'll just say a counter of 0. Maybe I'll call this IDX. So IDX of 0. I could say IDX plus the starting position. So that's our positional value plus 1. Or our index plus 1. Or index plus starting position, however you want to think about that. Divided by 6. Okay. So we can return the new list and see what that is. So this is process nums on the number list. Okay, what's happening there? So new list is going to get. Oh, I'm sorry. This is silly of me. I need to multiply this by the number, right? Each item in the list by its positional value plus 1, or plus the plus some offset. So I'll just call this offset. Maybe I'll call this offset as well, just to be a little more flexible in how I'm thinking about this. So offset. All right, so index plus offset over 6 times the number. So let's see what that gets us. Oh, what am I doing wrong? The first value definitely should be 0. Process the numbers. We pass in a list. New list, IDX 0 for num in list. The new list, new list dot append. We're going to append each of those values. I don't know why I'm setting that to equal. So what is going on here? I also need to say IDX plus gets 1. I'm sorry, my coding is a little bit off at the moment. Okay, that is working. Oh, I'm printing the num list above. Okay, let me just clear this one more time and we'll get a better look at the results. Okay. So here we get this list, right? Notice we're going to end up with floats. That just makes sense. We're going to end up with floats because of this division operation. Now, we don't have any decimal values, and you could say offhand, well, why don't we just cast that to int? We could, but maybe what I want to do instead of divide by 6 is divide by a denominator, and in this case, I'm going to just say pass in num list and set the denom to 6, which I'll do here. Okay. That'll get us the same result. But yeah, these are all floats. And so this is just a simple process. If we imagine taking this input list up here, it goes 0, 3, 3 times 1 over 6. Sorry, is that right? 3 times, well, yeah, let's print the original number list and just look at this operation on the original number list. So the first value is 0, of course that becomes 0.0. Second value is 3, that becomes 1.0. So if we want to like math this out, the number is 3, right? So 3 multiplied by the index, which is 0, plus 1, 0 plus 1, divided by 6 times 3. Okay. Weird. I would think that this would be 1/2. What am I doing wrong? Oh gosh. Index at 1. let's just print out our actual operation. IDX gets 1. Yeah, that would work. I'm just not sure why we're getting the values that we're getting offhand. Sometimes I, just have to get back in the swing of things. Let's actually map this out. Let's do IDX plus offset divided by denominator times num, and that equals this operation, which I'll plug in right there. And this is just me troubleshooting myself, maybe troubleshooting myself in the foot. And let's take a look at this. So 0 plus 1 is 1. 1 divided by 6 times 0 is 0. Yep. 1 plus 1 is 2. Oh, okay. No, it's working exactly as we expect. So 2 over 6, that's 1/3 times 3 is 1. Right? So really, we just shifted all the values in this list over by 1. Is that true? No, that is not true. But we did shift the first couple values. And then 3 plus 1 is 4. 4 6 times 9 is 6. So this all makes sense over here. I just was not realizing that our initial index is applying to the multiplication of 0. And so these results totally do make sense. Okay. So part of this is that part of the reason to use enumerate is this is convoluted, right? I need to make a counter, essentially an indexer. And, this gets pretty messy, and I probably would have noticed what was going on right away had I just used enumerate. So I'm going to refactor this to use enumerate. So I'm going to say for the index and number in enumerate the list, and then we'll say new list.append. And not only is this a little bit cleaner, it just it's easier to understand. And also I want to set an offset of 1, and maybe I'll just say instead of 1, I'll explicitly say offset. Does that make sense? So I'm passing in this offset value into here. So we can make a number of different values. Let's see. Oh gosh. And then I tricked myself again. Okay. So we're starting the offset at 1. So, there's no index. That makes sense. So in this case, we would actually want to start... No, this makes sense. Okay. All right. So this gets us our results if... Oof. Let's do this. Index. Index is the result of starting at the offset of 1. That makes more sense. Let's see what we get. There we go. All right. So for index and number in enumerate the list, right, which is 0, 3, 6, 9, and then the offset, which starts at 1 in this case by default, we're saying the value 0 is going to get multiplied by 1 over the denominator, which is currently 6. So we can take this idea and we can abstract it a little bit, right? So what if we change this to a 7 on the function call? Then we get, we get these other kinds of values, right? And that's completely fine, right? So we have some numeric operation that we can perform on any list. We're performing it on this range. All we're doing is taking some offset value starting at the first index of the list and dividing it by some denominator and multiplying it by each number in the list. This is a good use case for enumerate because you're starting at some value that is different from the index of the list. However, even if we started this at 0, right? Even if we started this at 0, we still have this association between the index and each item in the list. And we have it explicitly in these usable namespaces, right? IDX and num. So that's kind of the use case for enumerate. We can expand on this function a little bit. Why don't we consider the sum of this value? Okay. And I'm going to set this to 6 again. So what is the sum of these values processed through this function, right? This IDX over denominator times num. So let's find out. 6,545. All right. So let's look at that again. 6,545. Let's look at the sum for 7. 5,610. Let's look at the sum for 8. 4,908. Okay. So we see a trend there. What if we wanted to explicitly discuss this trend? So let's say in the range of denominators from 1 until 20, we want to see the sum of these values from 0 to, right, the sum of values from 0 to 100 going by 3s with different denominators in this multiplier, right? So, you know, if I look at a denominator of 1, I can say 39 to 70. Denominator of 2, I can see 19,635, and so on. Denominator of 3, we're going to see 13,090. So this might be a good use case for a dictionary. And maybe I'll create a dictionary. So this is going to be analyze denoms on num list. I'll just say nums, right? So in this case, let's pass in the original num list. So we'll pass in a list, and we'll have a low denominator, and we'll have a high denominator, and we'll just continue this offset, okay? So we'll think of the offset as being a constant. We're not going to modify the offset as we do this, but we can in a moment. So let's just take this whole sum right here, and let's explore this idea. So we have some dictionary, and I'm going to say for denom in range, low denom to high denom, I can go ahead and pack in the dictionary with the denominator, and it's going to get the result of this sum of processing the numbers on whatever this list is that we pass in, right? Oh, wait. How exactly do I want to do this? I want to do the sum of processing the list that's passed in with a variable denominator, and then the offset will pass that in as well. Okay. So let me just make sure my reasoning here is correct. And so this denominator is going to start at 1. We'll start it at 1. And why don't I just set these as defaulted for 1 through 20. Notice we don't want to start this at 0, right? Because then we're going to get a divide by 0. So I'll just go ahead and start at 1. Yeah, this should be fine. In some more technical way, I'd probably want to put parentheses out of here. Even though order of operations, this division will happen first because it's left to right, but just to be clear, we want to be clear about not having a divide by 0. We're not going to get one, but I just want to be clear that we're trying to avoid that. Okay, so we'll return the dictionary. Also, this is a completely novel problem. I'm just making it up as I go, but I'm trying to show that we can use this to analyze a new problem. I don't really know what the result of this is going to be, and so I'm kind of inventing a problem and then looking at the results of it. So I'll call to this function, and then I'll say for key value in d.items, let's just print the f string of the key and the value. And just see what we get. Oh, name list is not defined. Of course it's not, because this is num list above. So num list. Is that right? Let's see. Num list. Yep. All right. Okay. So let's kind of look at this and see if we can glean any information from it. Okay. So just notice we start at, we've got a 10,000 drop here, 6,000 drop, 5,000 drop. So we've got a slowing rate of change as we increase the value of the denominator. And remember, this value that we're seeing here is the sum of the digits that have been processed through our this kind of offset function we have over here. This index over denominator times the number. Okay. And then, yeah, so you can imagine we're going to bottom out somewhere here. Oh, I should probably do high denominator plus 1. That's probably what I would do in this case. Not a big deal, but notice we've got some rate of change here. And we could get this rate of change by just subtracting, we could subtract 19,635 from 39,270, and maybe that would just be, we'd represent it as the distance between 1 and 2. Distance between 2 and 3, we could subtract 1390 from 19,635. We could do that. We could sort of quantify this rate of change if we want to. But I'm not going to worry so much about that. I think what I'll do first is change this, when I call this down here, change this high denominator to 40. And let's take a look at, there's going to be a point where this bottoms out. Let me grab a screenshot of that. And yeah, so this is just an analytic approach, right? And I'm using a dictionary to get some idea of how this changes. Now, from a high-level view, I'm noticing something across this that shows my rate of change looking something like this. We haven't gone high enough in our denominators yet to see very fractional rates of change, but we could probably figure out the asymptote by either raising this number or by doing some more mathematical analysis, not procedural analysis. But since we're all about procedural analysis here, we can just see that this is an analytic approach, using Python. So that's kind of taking a problem and, some mathematical problem that we're seeing here, and we're taking some mathematical problem and we're just going ahead and working this and analyzing the results of it in the form of a dictionary. So let's do something else that looks kind of like this, and let's make this a little more we could make this a little bit more probability oriented. So actually, maybe I'll come back to more problems like this using enumerate and dictionaries after a bit. I want to answer some of these other questions first. So, yeah, why don't we... I'm going to move on to the next question, and then we can continually come back to this kind of like invent a problem, analyze it through a dictionary paradigm. So I'm going to answer this. Can I go over some probability stats questions that could potentially be on the technical interview? Yeah, so let's say, let me just make something up. Let's say you have 23 components in parallel. The probability of any one of these components functioning upon, let's say, 23 components in parallel that oscillate between being functional and not functioning. So this it's kind of a strange problem, right? And let's imagine that in this circuit of components, we need a certain number of them to be functioning at any given time for the circuit to be performing well. Like maybe they overheat and then they stop performing for some period of time, right? We're not going to quantify that necessarily, but what we can do is define a probability that at any given time, upon any given observation, there's a probability of it functioning, of a given component functioning. So the probability of any one of these components functioning upon observation is, let's say it's a fairly low probability. Like these are strange components for some reason. Let's say the probability of a single component functioning is 0.7. Okay. So what we can ask here is, what is the probability that all the components are functioning upon a given observation of the circuit? And then let's ask the question, what is the probability that none of the components are functioning upon a given observation of the circuit? So think about that. If you're watching and you think you have an answer to these questions, go ahead and throw them into the Slack thread. Oh, you know what? Let me add one more question in here. So imagine that at any time 10 of the components need to be functioning for the circuit to perform correctly. What is the probability that 10 or more of the components are functioning upon a given observation? All right. So this problem has some complexity to it, and we can go about answering it, I think, pretty steadily. First off, does anybody have a sense as to what distribution we might use or what distribution we might apply in this situation? If you have a sense of that, go ahead and throw it into the Slack channel. And I'm just going to wait a couple seconds for Anybody to respond to that? Not seeing any responses as yet. So I'm going to start coding something out before I answer any of this. And what I'll do is I'll take this whole thing and yeah, I'm seeing a correct interpretation of this third question. Yeah, we're going to use the binomial CDF here. It really makes sense for us to use the binomial CDF. And that the implication of that is that this whole thing we can consider through a binomial distribution. So in order to use the binomial CDF, I'm just going to code it from scratch. You might not necessarily need to do this on the technical interview, and if you do need to do this, you're not going to need to do it off the top of your head. We're going to give you the formulas to do it. So binomial CDF is going to require, well, I'm going to use the binomial PMF for the binomial CDF. Binomial PMF requires the combinations function, and combinations requires factorial. So I'll just code this out really quick. Factorial, everybody should know how to write factorial. The product is, well, I'm going to return a product of a given number n. It's going to be n times n minus 1 times n minus 2 times n minus 3, etc. And that down to 1, right? So I'll just do this for num in range. I'm going to just do from 1 to n plus 1. I could do 2 here. It doesn't really matter because anything times 1 is itself. And I'm going to say product times gets the number, and I'll return the product. So if I run this, factorial of 5, we should see 125. And I'll just move this down, and let's take, actually, oops. Maybe I'll just leave this up here for the moment so it's still readable because we're going to come back to it. And indeed, we get, factorial of 5 is 120. Did I say 125? I meant 120. My bad. Okay, so the next thing we need is combinations. So this is going to be all the different combinations of n choose k. This is going to be the n and k from the binomial PMF, where we're considering k successes in n trials. We're looking for the probability of k successes in n trials. But first we want to know how many different combinations would exist where we have k successes in n trials. Okay, so I'm going to return combinations of, I'm going to return int of the factorial. This is why I needed factorial. Factorial of n divided by factorial of n minus k multiplied by the factorial of k. This is the combinations formula. If we need you to write that, we'll provide you with the formula. And I'm going to utilize combinations in the binomial PMF, which is going to look like this. So I'm going to have a value of n, a value of k, and a given probability. Okay. Notice we're dealing with 0.7 as our probability. In general, we're going to see probability here. If we default it, we're going to default it to 0.5, considering coin flips, right? So I'll say binomial PMF, and this is just the combinations formula, n choose k, multiplied by the probability raised to the k, multiplied by 1 minus the probability raised to the n minus k. So we can answer this third question really quick. Let's do that first. What is the probability that 10 or more of the components are functioning upon a given observation? Remember, there's 23 components total. So I could code out the binomial CDF here. Well, why don't I do that? I'll just do that really quick, and we'll use the binomial CDF instead. So I'm going to say the binomial CDF, this is just going to be the cumulative probabilities across a range of k. So I'm going to say binomial CDF of n trials. We're dealing with a high value of k, the high value of k. This is generally how we do this. So this is going to be k equals 0 up to k high, the cumulative probability across all of those. And I'm going to, again, I'll just default the probability to 0.5. It's not really a good reason not to do that. So I have the cumulative, sometimes you see this as cumulative sum. I'll just say, sometimes I call this cumulation. I'll just call it cumulative to not be weird. And we'll say for k in range up to k high plus 1, this is going to go from 0 to k high plus 1. I'm going to say the cumulative value is going to be incremented by the binomial PMF nkp. Okay? All right, and then I can just return the cumulative probability. So how do I figure out this? Imagine that at any time 10 of the components need to be functioning for the circuit to perform correctly. What is the probability that 10 or more of the components are functioning upon a given observation? So what I can do is I can just say, to solve this, since I'm dealing with 10 up to 23, I can do 1 minus the binomial CDF, 1 minus the binomial CDF of 23 trials. K high is going to be 9, right? Because I want to include 10 in the result. So I'm going to say 1 minus the binomial CDF, 23 trials, 9 successes, right? So this is 0 successes, 1, 2, 3, right? And then I just take the complement of this. Remember, our probability of being functioning is 0.7. Oops. And I can just print this, and I believe this will give us a result that we're expecting. So that's pretty promising, right? The probability, and maybe I'll just drop this. I'll drop this in here, right? And I will grab this. I'll snag this, and I'll throw it in here as well. So here we're taking 1 minus the binomial CDF of 23 trials, 9 successes, and we're just wondering, right, what is the probability that 10 or more of the components are functioning upon a given observation? Okay, great. So I hope that makes sense for answering this question. Now these other two questions, they may seem a little bit tricky, I guess. So we can consider this like, what is the probability that all the components are functioning upon a given observation of the circuit? Now, because we're dealing with binomial, and maybe I'll just separate these questions out a little bit. So if we think about what binomial is, it is a series of Bernoulli trials. Okay? So if we have 23 components in parallel, which means that if they're independent of each other in some sense, right? If one of them is functioning, if one of them is out, it doesn't. We're assuming it doesn't affect some other component functioning or not. So if we have 23 of them, we can think of 23 as being a number of trials, and we can even take this to some degree to be binary-ish, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This is, there's going to be an occurrence where all of the components are not functioning, right? I'm sorry, this would actually be down here. We would consider this to be not functioning probably, if we're considering 0. Whereas all of these being 1, we might think of as being all the components functioning. Okay, fair enough. Now, if this was 0.5, we could just say well, the way we can do this either way. Component 1, what's the probability one of these components is functioning? Well, we know that. The probability of any one of these components functioning upon observation is 0.7. This is just 0.7 for the probability of one component functioning. What's the probability of two of these components functioning upon observation? It's 0.7 times 0.7. The probability of 3 is 0.7 times 0.7 times 0.7. The probability that all of them are functioning is 0.7 to the 23rd power. Okay. So that's that. That answers that question. And we could even throw another question in here that I'll answer next. So I'm going to put this in here. What is the probability that at least one of the components is functioning? Okay. This is actually just 1 minus this, right? This is every other case. This is every other possibility. It doesn't matter the component. This is just every other possibility aside from, oh, wait. I am saying that wrong. Let me put this below this. Sorry, y'all, I'm moving too fast for myself. So let's back up. So this is the probability that all the components are functioning upon a given observation of the circuit. We could ask the question, what is the probability that at least one of the components is not functioning upon a given observation? And this would be 1 minus 0.7 to the 23rd power. Okay? This is every other case. It doesn't matter which component or how many components are not functioning. This is every other case besides all components functioning, right? All the components, 0.7 to the 23, because there's a 0.7 chance that any given component is functioning, and we're observing it 23 times. This is a series of Bernoulli trials, and this, in fact, is just a simple multiplication rule. This is like, what's the probability of getting 2 heads in a row when you flip a coin? Well, it's 0.25. It's 0.5 times 0.5. It's 0.25. This is the same exact kind of problem, except we're checking component, checking component, checking component. We check 23 of them, so it's just 0.7 to the 23rd power. Okay, so what is the probability that none of the components are functioning upon a given observation? Well, what is the probability that one of the components is not functioning? That's 0.3. So we can just say 0.3 to the 23rd power, right? And then what is the probability that at least one of the components is functioning? Well, that's everything else. So this is just 1 minus that. We could answer these questions using the binomial PMF or the binomial CDF, depending. So I would probably do it with the binomial PMF. So why don't we do that for each of these as well? So I'm going to just grab this binomial PMF. And let's consider this first question. Let's print, oh, I think I'm already printing. Nope, I am not. Print binomial PMF of 23 trials. And then this is going to be, oh, whoops, I'm looking at the wrong one. So probability that all components are functioning, binomial PMF of 23. And we want to know, out of 23, what is the probability 23 are functioning? Well, this is just 0.7, isn't it? And then if we want to know everything else from that, it's just going to be 1 minus the binomial PMF of 23, choose 23. If we want to know the probability that none of them are functioning, this is going to be 23 out of 23 with a probability of 0.3, right? Because success in this case is that it's not functioning. And then we can take this a step further and say the binomial PMF, so 1 minus that is the probability that at least one of the components is functioning. So I'll move all of these to the top so I can actually run this. And yeah, let's just look at these results. So the probability that all of the components are functioning at any given time is very low, 0.000273. Notice that the binomial PMF is giving us the same exact answer. What's the probability that at least one of the components is not functioning? That's just 1 minus all of that, right? And binomial PMF here is giving us the same answer. What is the probability that none of the components are functioning? That's even smaller, which makes sense because there's a 0.7 chance versus a 0.3 chance, 0.7 chance of success, of functioning versus a 0.3 chance of not functioning. And what is the probability that at least one of the components is functioning? Well, that's very high. So this circuit is remarkably resilient, isn't it? If it needs, even though each component is intermittently out 30% of the time, we could say that we only need 10 out of the 23 of these to be functioning to be to have the circuit be functioning 99.8% of the time, given this layout. So this gives us some insight into parallelism for circuitry, I suppose. But it's also like we could adapt this problem in any way to any other binomial problem. So I'm gonna just put that code into the Slack. And so that's a type of probability question that you might see on the technical interview. Another considering whether or not to get into another problem in that regard. Yeah, I'll just do a really quick one. Comment all these out. So that was binomial. Let's do a Poisson problem. So I'm going to do Poisson PMF, and this is going to take lambda and a value of k, and we're going to return e to the negative lambda times lambda to the k, all divided by factorial of k. And to use this, we're going to need to import, I import e. You could import exp from math, either way. I do from math import e. I think in our materials we usually say from math import exp. Either way is fine. There's probably a good reason. I think there is a good reason to use exp over e, but I don't remember what it is. So let's make a problem here. Let's say in a given circuit with many components, with many parallel components, let's think about this. Let's say 5 components are in a failure state. Okay. Let's do 30 seconds. Okay. So let's first ask this question. What is the probability that 10 components are in a failure state in a given 30 seconds? So this is fairly easy to answer. We have our lambda here. Our lambda is 5. So I'm going to say we have a lambda of 5. And our k value is the number of components on which we're searching for the probability, right? So that's going to be, I'll just call that k. Our this expectation we have on any observation is going to be 5, and we're looking for the probability that 10 is occurring in this volume of time. Does that make sense? So with that in mind, I can just say I can print the Poisson PMF of lambda, which is 5, and k, which is 10. Okay, so let's find out what that is. 0.01832, etc. The numbers to the far right of this start getting less meaningful. We want to choose some level of precision. I usually do 3 or 4. Okay, so let's turn this question a little bit. Let's say the circuit needs at least 20 components to be functioning at any given time. What is the probability that 23 components are functioning in I don't know, 50 seconds? Now, if this question seems obtuse, well, good. This is not an answerable question. It's not. Notice in our original problem statement, we said on average 5 components are in a failure state every 30 seconds. The circuit needs at least 20 components to be functioning. We don't know how many components are in the circuit. So we don't know how to answer this question. What is the probability that 23 components are functioning in 50 seconds? This actually doesn't have any meaning at this point. So I'm going to say just unanswerable given our current understanding of the circuit. We need more information, and that's fine. We need some average number of components functioning, right? But we have a lambda for the number of components that are in a failure state in 30 seconds. We need something that tells us how many components are functioning in a given span of time. So we can't answer that question. Let's come up with a question we can answer that looks like the kind of Poisson question that you might have to tangle with. So I'm going to say, I'm going to ask, what is the probability that more than 10 components are in a failure state in a given 50 seconds. Okay. So notice when you see something like more than or less than, that's when we're starting to think about CDFs, right? Because this is effectively going to be the probability of the Poisson PMF of with our lambda's 5, the probability of 0, plus the probability of 1, plus the probability, etc. Sorry, I said our lambda's 5. That's not actually true anymore. So why don't I fix that first? Notice we're dealing with a different span of time. We're dealing with 50 seconds. And in our original lambda, we were dealing with 30 seconds and 5 components. So the way we can recalculate this is 5 components multiplied by 50 seconds divided by 30 seconds, right? That makes sense. Since we are in ratio, we have increased our span of time from 30 seconds to 50 seconds. well, that's going to be a 5/3 increase of our lambda. That's an assumption we can make because we're assuming independence between all the components. So with this in mind, let's, I should probably have done this, lambda and k. So our new k is going to be, it's still 10, sorry, actually. So we're trying to figure out this value for a high k of 10. Actually, our high k is going to be 9. No, sorry, our high k is 10 because I'm saying more than. If I would have said at least 10, that would be 10, 11, 12, 13, 14. But actually, I'm saying more than. Since I'm saying more than, then I want to consider all values of k from 11, 12, 13, 14, 15, 16, up until infinity. Well, that's a lot of computation. I'm not going to throw a k of infinity in there. I'm going to instead take the CDF and I'm going to subtract the CDF of 10 from 1. So how do we make the CDF? That's easy enough. It's just a simple accumulator. I'm going to say, maybe I'll just make this all look a little bit nicer really fast. Okay, so I'll do def Poisson CDF, and I'm going to do a lambda and a high k. Remember, it's going to be inclusive of the high k. I'm just going to call this accumulator. Maybe I'll call it proba. It's kind of nicer. And that proba is going to start at 0. I'm going to say for k in range, and I'm going to go from 0 to the high k plus 1. With that in mind, I'm going to just increment our probability using the Poisson PMF of lambda and k, right? This time I'm pulling k from there, and I've got my lambda up here, so easy enough. So I'll return the probability, and let's do the Poisson CDF here. Poisson CDF of lambda, high k, and I'm looking for everything greater than 10, so I can print 1 minus the Poisson CDF of lambda and high k. And I'm still printing the above thing, that's fine. What is the probability that more than 10 components are in a failure state in a given 50 seconds? Well, that's 0.219, roughly. Okay. So those are the two main kinds of distributions problems, and some sort of simple multiplication rule, basic probability problems. I'll throw that in the Slack as well. I do kind of want to set some of these aside. Making up questions, I can make up questions all day. It's kind of, I don't know. It's something I'm good at, but you know what? I'll just delete the whole thing. Okay, so if you're interested in random variable problems, there's a notebook that I'll go ahead and share in the Slack. Yeah, I'll share it in the Slack. It's something that we teach out of Premium Prep starting very recently, and I think it's helpful. Let me say that. I think it gives a really nice tour of problems that I'll just say are kind of harder than what's on the TI. So I'll open it up here, and let's take a look at some of the things inside of it. So this is from the most recent Premium Prep. I think I wrote this on the spot somewhat. There are a ton of binomial problems in here. There are a ton of Poisson problems in here. And then we've got these random variable problems. So this is the kind of problem you might imagine on the technical interview in terms of random variables. So why don't we just look at it really quick. This one's pretty easy, but you do need to do a little bit of verification. So you consider a random variable z. Z is 0 when the sum of a 6-sided die and a 36-sided die is even. Z is 1 when the sum of a 6-sided die and a 36-sided die is odd. So the question would be, what is the probability that 3 successive dice rolls result in this sequence of outcomes? Z equals 1, Z equals 1, Z equals 0. It turns out, upon a little bit of analysis that can be proven here, that Z equals 0, the probability of Z equals 0 is 0.5. The probability of Z equals 1 is 0.5. We can see that by just building the sample space. And so the probability that we get 1, 1, 1 is 0.5 times 0.5 times 0.5, which is, of course, 0.125. There's a trinary challenge here. If you understand these kind of random variable problems, I think you'll be sitting in a good spot for the technical interview. So I'll just drop this link in the Slack. I'm not going to go over more of these at the moment because I think there are more questions I would like to get to that I'm seeing pop up. Okay. And probably at the when we wrap up, if I have time today, I'll go over some enumerate stuff. Again, some more enumerate stuff. If not, we can get back to that on Friday. Okay. Can we do the final challenge in the enumerate function section of list iteration? Yeah, why don't we take a look at that? Just waiting for it to load. Okay. The final challenge, let me reset that input. Okay. So we've got write a function called alt series. This function should have one parameter, which is a list of numbers. The function should pack in a variable called alt sum. That is a sort of looks like it's an int accumulator. Another variable called power sum. Okay, yeah, so why don't let's do this. I think this will be a nice little exercise. All right, let me see. I'll probably record myself making this solution so that I can just append it into our Learn materials after I'm done. So hopefully I don't screw it up too bad. All right, so write a function called alt series. This function should have one parameter, which will be a list of numbers. Okay, so I'm going to just start with that. I'm not going to read through the entire thing first. Not saying that you shouldn't. I just like to sort of build my scaffold as I go and then go back and make sure. So alt series, which is going to take a list of numbers. I'm going to call this numList. And in a variable called alt sum together all the numbers in numList. Okay. So alt sum. Sorry, alt series. That should be alt sum. My bad. Alt sum. This should sum together all the numbers in. Oh wow, this is a little more complex. Let me just snag all of these. And I'll just put them directly into my into here. Okay. So in a variable called alt sum together all the numbers in numList. Okay. Where the values with even indices are added and the values with odd indices are subtracted. So why don't I start with that? And my suspicion is that I'll be able to do this part sort of in follow-up. So if I'm considering both an index and a value, that's a good use case for enumerate. So I'll just say for index value in numList, this is going to be enumerate. And I'm going to say alt sum. Oh, sorry. If the index, this is the even indices. So if the index modulo 2 is 0, if it's evenly divisible by 2, then alt sum is going to be get the value. This is a kind of simple accumulator right here, a simple accumulator. I also need to initialize the variable, easy enough. So this should be all the indices are added. Oh, or the odd values should be subtracted. Okay. So why don't I do that as well? Okay, this is the logic to complete alt sum. So we've got another variable called power sum. And power sum is going to sum together the result of raising each value to the power of its index. Okay, that's easy enough. Sum together the result of raising each value to the power of its index. So again, simple accumulator. No matter what, I'm going to say power sum is going to be incremented by the value to the index, right? Okay. In a variable called index sum together the result of raising each index to the power of the value at that index. Okay. So we're starting at index 0. That's nice. So we don't have to worry too much about that. This is index sum. So I'll go ahead and say index sum. We initialize that to 0. And index sum, again, is just this simple thing. It doesn't take much logic. This is just the index to the power of the value, I believe. So in a variable called index sum together the result of raising each index to the power of the value of that index. Okay. The function should return 3 variables in this order: alt sum, pow sum, and index sum. So I'll grab that out of the description and I'll just say return all of that. I'll clean this up a little bit and we can take a quick look at this logic. So in general, I think it's nice to run this locally if you have some expectation of the outcome. We don't, but why don't I just run it locally anyway? I'm going to just say from the range from 0 to 100, and I'll print the alt series of this. We should see a tuple of alt sum, pow sum, and index sum coming out the other side of it. So why don't we take a look at that? Okay, well, that's what we get, -50, and then this massive number, and then this other massive number, which looks a lot like the first massive number, doesn't it? Is that how that works? Well, let's find out. Let's see if we get an error on this, and if we do, we'll troubleshoot it. So this is the enumerate function challenge. Oh, sorry, there's a couple tests I can run right here. Why don't I just run those, and we'll troubleshoot them if there's any issues. So I'll just print this, print that, and let's see if we get what we expect. -4, oh, 4330, and 6626. Oh, that's... So I'm getting the correct thing for this second alt series, 046. Oh, I'm not. Okay, let me look at this problem statement just a little bit more. In a variable called alt sum together all the numbers in numList where the values with even indices, right? If index modulo 2 is 0. So that first value, I think we were getting correct, right? Let's just double check that. 4, we're getting -4. We're getting 0 here. I must be doing something a little bit wrong here. Where the values with even indices are added and the values with odd indices are subtracted. You know what? Let me run this, because this logic, I think, is following the description, but maybe these tests are wrong. In all likelihood, I'm wrong. Oh, I am wrong. Huh. Interesting. Okay. I wonder if there's an issue with this challenge. Is anybody seeing a logical error that I'm making here? Because looking at these rules, well, let me go ahead and stop recording a solution to this, because there might actually be a problem with this function, or there's a problem with my reasoning. Okay, so we're starting alt sum at 0, right? We're summing together all the numbers in numList, where the values with even indices are added. The summation index should start at 1? Oh, cruel, cruel world. Okay. Okay. Well, dang it. That's what I get for not copying everything. All right, let's see. Let's see if that works. Dang it. It does. Okay. And this actually looks nearly exactly, the explanation given here looks nearly exactly what I have over here. Thanks for the catch. I probably would have looked at this later and I would have been fairly disappointed in myself for not being observant. Thanks. Okay. There's a request to go over the concept of a list comprehension. So why don't we do that? Why don't we consider a list comprehension? And why don't we use this alt series to do so? So we've got this function, and yeah, I think this is good. Let's go with this. So maybe I'll do a couple things here. But the first thing I'll do is list comprehension. So I'm going to think of something variable in here. Maybe I'll just think of numList as being variable. And let me think of a good way to do that. Maybe this doesn't lend itself. No, this works. Okay. First, I'm going to just write a for loop. So I'll say for let me generate a list of lists. How about I do that? So I'm going to just call this list of lists, and I'll make it empty first, and I'll say for I in range, let's do 20. And this is we're going to pack in 20 lists into this list of lists. And we don't actually, well, do we need this I? Yeah, why don't we use this I? And I'll say for j in range, and I'll do I plus, what should we do? I plus, why don't we do this? Let's do for incrementer in range, and we'll do 0 up until 10. How about let's do that? So let's do list of lists dot append, and we'll append a list that goes from a range of 0 to let's do 50. Let's do 100. and we'll go by the incrementer. So we'll start this at 1, and we'll go up to 10 plus 1. And first, let's see what this gets us. So let's print this list of lists and see what data we're working with. Actually, let's do this. Let's print for list in list of lists. Let's just print each list. Okay. So in this first one, of course, we go from 0 to 100 by 1s, and then we go to 0 to 100 by 2s, 0 to 100 by 3s, and so on. So that should be fine, I think, for what we're doing. And let's first think of what we can do to transform this into a comprehension. Okay? So what I might try to do, and let's just see if this works. To transform this into a comprehension, I'm taking the internal part of this, and I am then saying for incrementer in range, and then I'll do 1 to 10 plus 1. And then let's go ahead and print that and see how that goes. Oh, I need list of lists to live out here. Okay. So we're getting all these nones. Now, this is a classic non-use case for comprehensions. I want to perform this operation over and over again, and I'm trying to get a list for each of these when, in fact, this accumulator pattern is probably what I should use. So what I could do instead, for each of these lists, I want to get some kind of, let's say I want to get these tuple values out. What I'm going to do here is I'm just going to grab this alt series. There's a return from this function call, right? And I'm going to use that to pack in a new list from this list of lists. And I'll go ahead and say, I'll call this alt sums. And I'll just say for sum in alt sum, actually for tup in alt sums, because remember these are tuples. Let's print the tup. And what we get out of this is what that comprehension has done for us is it has created a new list, right, that has the results of these things. So this is a little complex. Why don't we back up and just do a comprehension? Just the most basic comprehension. Num for num in range 10. And let's print that. And we get 0 through 9. That's what we're getting. I'll do that again so you can see it up here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Range 10. Let's go from 0 to 10 by 2s. And I don't think it'll be too surprising. We get 0, 2, 4, 6, 8. So use cases for comprehensions. We don't have any sort of modification of a data structure here. We are creating each one of these operations that happens in the comprehension can happen independently of each other one. Whereas, remember what we did, what I tried to do through list appending, right? So we have some list. If we were trying to say list dot append that number, watch what we get. We get none, 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 none. This, there's no return from the append method. Now, what if we just try to print the list? We do get some result from that. Okay? So, if you want to perform this repetitive append, you don't expect anything to occur. Like the result of this is not the same as the result of the operation on the list. That may seem a little confusing, right? So if we try to assign this comprehension to a new list, well, append doesn't return anything. But we have modified the original list. So if we print new list as opposed to the list itself, we're going to see two different results, right? Okay. So I hope that's not too convoluted. Essentially, the way to think about a comprehension is you've got some repeatable operation, and the those repeatable operations are independent of each other, right? You don't have necessarily an accumulator in here, but you can still use this for accumulation of sorts. So let me show you a good example of that. Let's say you want to sum the numbers between 1 and 1,000 going by 13. Okay. You can do this with a comprehension. You can say num for num in range 1 to 1,000 going by 13. And then you can just apply a summation across all of this. This is very Pythonic. This is a nice way to use a comprehension. Turns out that's 38,115 if you ever wanted that piece of trivia. Okay. All right, so we're about at an hour and a half, and in general, study halls are going to be an hour and a half to 2 hours long, you know, just to answer questions and everything like that. We'll lecture or cover specific topics from time to time, but in general, we're here to support you in the places where you're stuck. And yeah, feel free to keep asking questions in DS Basic Prep. The next Galvanize study hall will be Friday at 4 p.m. Mountain Time, 3 p.m. Pacific, 6 p.m. Eastern Time. And bring your questions. If there's something more general you want to go over, you know, bring it up. Maybe message me beforehand. Cool. Thanks so much, everybody. Have a